computer's thinking. Okay, parametric equations. Now, the truth is, what we do today, we're not doing a ton with these parametric equations. But I know that if you ask the calculus teachers, they would say out of everything we're doing in this chapter, this is like the most important thing for them. In a way, conic sections are good topics for math, and they're good topics for a certain level of algebra. But you don't do much with them in calculus. It doesn't mean we shouldn't do them because it doesn't point directly at calculus. But that's why I'm a little reluctant to give that up. I think if they had to rank order what we've done in Chapter 10, this would be number 1, probably polar coordinates would be number 2, and the conic sections as a group would probably be number 3. But like I said, we won't do a ton with this, but we will do some. So, let me get my calculator going, because you definitely want to have your calculator. Going. So parametric equations. When we have y as a function of x, we know that can be graphed in the coordinate plane, right? I mean, if you didn't know anything about the function, you plug in a bunch of x's, you calculate the y's, you plot the points, and you get a graph. This particular function is a parabola. It opens down because of the minus. Its vertex is at 2, 4. So that's what I'm drawing right there. And I've stopped it at the x-axis. So that's the graph. Give people a chance to catch up. Okay.
Good morning, Tickettown Warriors. This is Mr. Monica. May I please have your full attention at this time? Teachers, I sent you an email a few moments ago. Could you please look at your email?
Okay, now if that same graph represents the result of some real-life process, like the path of an artillery shell or a baseball, goes up, comes down, and that is actually the path that it follows, then just looking at the graph, that static graph, it doesn't really tell the whole story, right? Because it didn't just have the entire graph all at once. It actually started here, and then it went up, right? And it went down. Right? So the graph isn't complete just to show this is the path that the baseball took. You really kind of need to know what direction did it go, or artillery shell. And so that's what we're going to get with parametric equations. It reminds me of this story when I was going to Kansas State University. That was the first school I went to, and I was taking, probably it was differential equations. And it was being taught by this crusty old professor from Arkansas, Mr. Sloat, or Professor Sloat. And but he had this German guy that was his assistant or something. He was an old guy too. And so they were talking to us about quadratics and the shapes of the graph and things like that. And Sloat, the American professor, he goes, I was, in charge of targeting artillery shells during World War II, and we used this stuff, to target the shells. And he said, I don't know if it worked. And these guys must have practiced this, because then the German guy with a really heavy accent would jump in and say, it worked, because he was on the other side of that. But, so anyways, parametric equations are when actually the x and the y coordinate themselves are depending on some other variable, and the other variable is what you call a parameter. And most of the things we deal with, it's time. Time is another variable that both the position, the x position, the y position, they depend on time. Once you know the time, you can figure out the x and the y and plot the point, but you need to know the time first. So this is an example. It's like before their example where they show, here's a parabola that opens down because it's quadratic and it's got a minus in front. And this would be the shape of the graph. But it actually, each x and y both are functions of t. And here would be the functions of t. They're fairly complicated, but, so the variable, that third variable that both x and y depend on, those are called parameters, right? Like I said, most of the time that'll be t. Not quite all the time, but most of the time that's t. The equations, x as a function of the parameter and y as a function of the parameter, are called parametric equations. Right. The graph of parametric equations, it's got the same shape as the graph of the rectangular equation, but it's got arrows on it to show you which direction that it gets drawn, right? You add the arrows to show this is how the graph was drawn as the parameter increased. In this case, as t went from 0 to whatever it did, let's see, until it got to that point, and then it stopped. So those are, okay, and I should say, the graph is called a plane curve. So parametric equations, plane curve. So we do a couple things with this. Number one, we will graph parametric equations. And number two, we will eliminate the parameter by combining these two, right? Combining these two to show that it equals that. That's really all we do with them. Now, in my former life, right, when I was studying meteorology at a pretty high level, and we used equations to model the atmosphere. We had 7 equations with 7 variables. They were not linear equations because, that's why you can't solve them for one exact value. They were partial differential equations, and they were parametric equations because they all depended on t, right? You don't want to copy this stuff down. This is just a couple of them. These are the what you would call the horizontal momentum equations. And by horizontal, we mean U is the speed of the wind, east and west. V is the speed of the wind, north and south. But they're all considered horizontal, right? It's in the flat plane here. And you can see somewhat of the balance of forces here. This represents a derivative, what you call a derivative in calculus. Notice that the D is kind of a normal kind of D. But this is called a full derivative, Lagrangian derivative, which equals all of this stuff here, right? And this kind of curly D, right? That's what that's supposed to be. That's called a partial differential. So when you said differential equations, that's the kind of thing you're dealing with. What basically it says is, how the wind is changing, how this component of the wind, the one that's going, east and west, changes. First, it depends on, well, how is it changing right at one point in space, right? If I just sat there and measured, what's the difference, from now and the next minute? How did it change, right? The next term is representing how much is it changing in X? I mean, how much is the wind different? Let's say I've got a wind speed of 10 knots there, and over here I've got a wind speed of 20 knots there. So it's changing in the X direction. right? So this is saying how much is it changing in the x direction, and then multiply it times the wind. So if, for example, there was a wind here that's blowing that way, you might think that it's going to blow lower winds towards this direction. That's called advection, right? So that's what this here is. So you can advect wind in this direction. You could advect winds up or down. This is vertical, right? Change in vertical. P is what we use at pressure as a vertical coordinate, and omega is the wind speed. It's a little more complicated than that. This is pressure gradient force. You know, you expect when there's like a low pressure there and a high pressure there, you know, we expect that there's a force that's going to make the wind blow like that. That's what that term is, and that's the Coriolis force. In fact, we saw. I think I had this up there. I mean, it's all going on right there. You can see that that tropical storm Ana is sitting right in there. So, you know, what is it making the winds go around like that? Coriolis force. The pressure gradient should be blowing. If this is relative low pressure, and it is, you would expect that the winds are all blowing in towards the center. And it's not, right? The winds are going around like this. Why is it? Coriolis force, right? And there's more equations. I didn't write them all in here, but I mean, these are parametric equations. It's what you use. In real life, you could probably use parametric equations, right? This has to do with, as I recall, this is all about condensation and evaporation and all these kinds of things that go on in the weather. Actually, no, that was thermodynamic energy equations. You know, dense warm air rises, cool air sinks, things like that. This was condensation and evaporation. That's another part of it. But they all have T in it. They all got this parameter that everything depends on T. This is vertical velocities as a matter of, you know, function of pressure gradient forces and things like that. So basically what you do with that stuff is you learn about the math behind it, right? The math behind it is describing, you know, how is this graph changing at any instant on the graph, right? Now, in the real world, you know, I can't deal with infinite change, right? I end up having to convert these into like fixed points and then just approximate what's going on by a slope formula kind of thing. But, you know, parametric equations are important. And I could tell you that in calculus, one of the things that they struggle with a little bit is that students not understanding just the very concept of rate of change. And rate of change just means slope. I mean, that slope is just saying how something is changing. You know, but if I have an equation in the atmosphere that deals with pressure, I mean, what am I really measuring on that? What am I really interested in? I want to know how is it changing. I mean, I can go out there and measure the pressure today and see what it is, but what do I want to know? I want to know how's that going to change. So rate of change, slope. Even when the slope is not the slope of a fixed line. Even when you're talking about things that are described by not y is a function of x, but parametric equations, x is a function of t and y is a function of t. So sketching a curve, a plane curve, right, that's described by these parametric equations. You're going to have to draw a table of values, right? You have to make a table of values. Now, in this case, we've got x is a function of t, y is a function of t, and then what does this look like here? Domain, you know, what always comes at the end of the statement like that? A domain statement, something that's telling us the values of t we're supposed to plug in. Because now the independent variable is t. It's not x, right? It's t. X and y both depend on the t. So given that domain, you can see in their table of values that they have t equals -2, and they've taken, you know, integer values from -2 to +3. And then these values of x and y are just what you get when you plug in here. Like if I plug in t is -2 here, I'm going to get -2 squared minus 4. 4 minus 4 is 0. Right? If I plug in -1, -1 squared is 1. 1 minus 4 is -3. And so this whole table of values was created by plugging in these values of t into these two equations. Now, these here, these are the points in the plane that you're going to graph, right? X, Y. So the first point, when t is -2, is 0, -1. The second point is -3, -1/2. So -3, I can't see. These must be every 2, yeah. So this is -3, -1/2. But there's a direction because this piece of the graph was drawn as t increased from -2 to -1. So there's an arrow that shows the direction of the graph of the plane curve, right? And the next point, -4, so 0, -4, -3, 1/2, 0, 1, and 5, 3/2. So these are the points that we plotted in order: 1, 2, 3, 4, 5, 6. So we draw arrows to show that that was the order of them. So that's called a plane curve. Now, I'm not sure it makes much difference, but x equals t squared minus 4. Would you say that x is a function of t? It's a parabola, opens up. Y-intercept is -4. Yeah, that would be a function. How about this one? It looks like it's linear. Y equals t over 2. Sure. Is this y as a function of x? No, it's definitely not. Wouldn't pass a vertical line test. Okay. So let me see what I got next. Okay. So sketch the plane curve given by the parametric equations. Now, you can do this in your calculator. I mean, if you just want to get the table of values. I mean, if I go to y equals, just to show you, right? This is what we normally look at in the calculator, right? When it's just at default mode, that's what it looks like. Now, go to the mode, and notice on the third line down where it's highlighted on function right now, but right next to it, it says PAR for parameter or parametric. So you go down to that one, enter so that it's highlighted on the PAR, and now go back to y equals and see what it equals, what it looks like. Okay, now you've got x1t, y1t. So x is a function of t and y is a function of t. Okay, so let's say I'm going to put on the first line, x equals 2t. No, I don't have her in any class. Yeah. Now notice that in order to get the t, you still hit that same x button. No, that x button has actually got 4 variables on it, right? It's the first one is x, but the next one over is t. So when you set it to parametric and you hit that, that brings up the t. Right? Enter. And this one, for the y, 4t squared. 4t squared plus 2. Okay, now you can graph. I can hit graph and see what it looks like. Let me do zoom just to get a normal looking graph. That looks kind of crazy. But they have given us a domain statement right there. So I think what I would do is let's go into the table of values and see what the x, the range of x and the range of y values that we should set for our window before we draw the graph. So go up to the table set right here, second table set, and we're going to have it start at -2, and it's going to go in increments of 1. Okay, so now let's go to the table. So it looks like the x values from t equals -2 to 2, the x values range from -4 to 4, right? So we definitely want to have our x, when we set our window, we want to set the window to go for x equals -4 to 4. And it looks like the y values go from 18 down to 2, and then they go back to 18. So let me go to the window. Let's remember those things there. -4 to 4, 18 to 2. And the t is -2 window. So the t min was -2. The t max was 2. Enter. This, we wanted to step every 1. We went from -4 to 4, and that can be every 1. And then it went from 2 to 18, so I guess we'll start at 2, and we'll go to 18. And now when I draw the graph, that's what it looks like. Now, which direction does it go? If I was going to sketch that curve, I mean, it would not be notice that it's giving us these blocky kind of things there. I'm sure it's a smooth curve, but which direction? Do the arrows go this way or do they go the other way? Hit trace. Right? Trace is going to pop up the cursor at the beginning, and now when you go to the right, you'll see the direction. See it going? I'm already too far. So go back to 2. T is -1, T is -2. So right now it's at -2. It's right there. So I hit 1. There it is. Go again. There it is. Go again. There it is. Go again. There it is. So the direction of the plane curve is like that. Okay. So what I would encourage you to do is go ahead, you take your table of values from the calculator, write it down, sketch it, smooth it in, and draw the arrows on it. So draw a plane curve. If not, then you just do it manually, right? I shouldn't have done that. T, X, Y, -2, -1, 0, 1, 2. Too many rows, right? And then plug them in, calculate them individually. But you can let the calculator do that part for you too. Just definitely fill in your table of values, sketch a curve. Okay. Right. The only other thing we're going to do with this is the eliminating a parameter. So if you have 2 parametric equations, then we want to know how is it that we eliminate the parameter. Well, it should remind you a lot of solving systems of equations with substitution, right? With substitution, you solve for one equation for one variable and you substitute into the other. Okay, we're going to solve one of the parametric equations for t, the parameter. And then we'll substitute for that in the other equation, no more t. Solve for y. Or sometimes you don't solve for y, but you just have to see. And we did this a little out of order because, usually you do parametric equations and then you do polar equations. And in the polar equations, they start using this rectangular, to describe what is it when it's x and y. But actually that started on the section before. We just flipped the order. So let's do one of those. Sketch the curve represented by the equations. Actually, I think I cut off part of that. I'm gonna change these to just say eliminate the parameter. So eliminating the parameter means we're going to solve one of these for the parameter, and then we're going to substitute in the other. So now you got to decide, well, which one do you think would be easier to solve for the parameter, or which one will make it, you know? Yeah, I mean, this one's got the square root in it, so you're probably instinctively you're going to say, how about if we do that one, right? So let's solve this one. So how would I solve? Oh, actually, okay, we can. I mean, it's no problem. We'll do it like that. So how am I going to solve that for t? I forgot, that's a t, not a 1. So actually, you've got 2 t's here. You only got 1 t there. That's how you can see which way does it work out better. Right? If I'm going to solve this one for t, I mean, first I'm going to multiply by t plus 1 here. Now I've got t's on both sides, and I need to get them together, right, somehow. Because I can't solve for t unless I get it into one term. Right? So this is going to look like t plus 1 times y equals t, means ty plus y equals t, which means ty minus t equals negative y. Right, so I subtracted the t to this side, I subtracted the y to that side. Now I can put these together by doing t times y minus 1 equals negative y. T equals negative y divided by y minus 1. Which I would, personally, I would say, well, I don't want to have all these negatives going. How about if I switch the order of y minus 1? I'll make it 1 minus y, which will allow me to make that a positive. Right? Switching the order of subtraction makes it opposite. So this is the same thing as y over 1 minus y. Okay, so we've done that. Then what? Right? Now we're going to plug that in here. Right? So that'll be x equals 1 divided by the square root of y over 1 minus y minus, where am I at? Plus 1. So now, I mean, we have to solve for y. I mean, you know that it's going to end up having to be y as a function of x. We want to recognize the shape of the curve. Let me do this before I make any more writing on here. Copy, paste. I'll go back here. I mean, it's not a big deal. I mean, you got to get rid of the square root, so you square both sides, right? So now we've got x squared equals 1 over y divided by y minus 1 plus 1. Yeah, it does get confusing. I didn't even write that correctly, did I? You know, although I think it's, you know, it's definitely doable. You can multiply to get this up here and bring the x squared there and then figure out a way to multiply through by 1 minus y and get all the y's together. I think if we would have solved it for t here, we would not be going through this mess right now. So let's see instead, let's try to solve this one for t and plug it into there, and we'll see how it's much easier. At the very least, you know, what's going to happen? It's going to be already solved for y, which is kind of where we want to go. So let me do this. Let me get rid of, oh, that doesn't work. Edit. Okay, so solve this one, right? Again, square both sides. X squared equals 1 over t plus 1. T plus 1 equals 1 over x squared. T equals 1 over x squared minus 1. That's a very bad T. Okay, so we did the first step. We solved for the parameter. Now we're going to substitute into the other equation for that parameter. Y equals 1 over x squared minus 1 divided by 1 over x squared minus 1 plus 1, which in the denominator, the 1's cancel. Y equals 1 over x squared minus 1 over 1 over x squared. And then if you're dividing by a fraction, right, that's the same as multiplying by the reciprocal, right? So this will be 1 over x squared minus 1 times x squared over 1. And you distribute, right, this x squared times 1 over x squared equals 1, and negative 1 times x squared minus x squared. So what is the shape of that graph? It's a parabola, right? It opens down, y-intercept is 1. Now, if I was going to graph that, if I was going to sketch the graph, now I remember why that part was in there. If we're going to sketch this graph, then you might say, right, we expect that to be a parabola that goes like this. The problem is there's a limited domain here, right? You're not going to have x values and y values of any value here. I mean, you've got to have that t has to be greater than negative 1, right? The domain, because you have you're dividing by a square root. You can't divide by 0, and you can't take the square root of a negative. So we should say right away here that t is greater than negative 1. You can't equal negative 1 because then you'd be dividing by 0. Actually, over here, you'd be dividing by 0 also, right? Which means, what's the least number you're going to get here? If t is just a little bit bigger than negative 1, then this number is positive, and you take the square root of a very small number, 1 over that number is going to be big, right? So that's going to be like infinity. That means this graph is actually starting and where x is infinity over here. It's probably going to be doing this kind of thing. All right, the y value, if I had to plug, I can't have negative 1, but if the t starts greater than negative 1, let's say for the first y value, it would be 0, 0. Is that right? Yeah, well, at 0, in between negative 1 and t equals negative 1 and t equals 0, this thing's going from somewhere over here to, at 0 would be 0 over 1, which is 0. So that's got to be like this piece of the graph right there that got you to y equals 0. I guess, with these parametric equations, we could actually like put those in and see the graph drawn. But I'm pretty sure we know what the shape is because we know that in rectangular coordinates, we know what that is. And I think we would have to like actually plot some points and see the graph doing this kind of thing. Right? As the t got very large, as the t gets very large, then this number, actually, what is the, could x ever be negative here? No, I mean, this is always positive. The square root, that's always going to be positive. Can x ever be 0? No, because the numerator is not 0, so this is not going to get as far as x equals 0. It can get infinitely close to that as t gets really, really large. Then you'll be dividing by a really big number, so it's a fraction. But basically, what it's telling us is that this thing, right, cannot have this piece of the graph. In fact, it's not even going to touch that point right there. It's going to have to look like this. It's got to be an open circle for x equals 0. So it starts down here and it gets up there, and that's as far as it goes. Okay. But main thing is eliminating the parameter, just understand. Solve one for the parameter, plug it into the other. Now, this one is saying eliminate an angle parameter. And that is a little bit different. And there's a couple of problems like this. So you want to know how to do that. You do not solve for theta and then plug it into the other one. Instead, watch what we do here, right? This one is x over 3 equals the cosine of theta, right? This one, y over 4 equals the sine of theta. Right? If I square both sides here, now I've got x squared over 9 equals cosine squared theta. And I'm going to write it right underneath here. Y squared over 16 equals sine squared theta. You see all that? So I solved for the cosine, I solved for the sine, I squared both sides. Now I'm going to add them together. Okay, what do I get on the right-hand side when I add these two together? Sine squared plus cosine squared, which equals 1. So in that way, you eliminate the parameter. See that? So this is going to be on the left. It'll look like x squared over 9 plus y squared over 16 equals 1. Which is what shape? Say again? It's an ellipse, right? So these two parametric equations, where the parameter is actually theta, right, an angle, actually those two together, they're describing an ellipse. Center is at the origin. It's vertical. So there's a couple like that, and you want to do the same thing. Isolate the sine and the cosine so you can square them and add them up. And when you square them and add them up, what do you get? 1. So let's see. We evaluated sets of parametric equations. We graphed the curves, the plane curves. And then we eliminated the parameter. That's it. So all of these say graph and eliminate the parameter. So I would do the table of values for t, x, and y, and sketch the graphs, and then eliminate the parameter.